Thank you all for coming to this year's Wulff lecture. So before we start, I just want to spend a couple of minutes just talking about where this lecture series comes from. So it's named in honor of late Professor John Wulff, who is, of course, a very passionate educator and researcher on material science and engineering. He actually started 3091, the Introduction to Solid-State Chemistry class, which I believe many of you have taken or are actually taking it. And I'm going to show you a photo of him actually in a 309 lecture. And he's obviously a very dynamic and passionate lecturer, as you can tell from the blur image of his hands in this photo here. So this lecture really is trying to sort of spread the love for material science engineering, try to inspire the next generation of material scientists and engineers. And for that, this year we're actually very fortunate to have Professor Chan from University of Pennsylvania here with us. She is the inaugural Dean of Innovation and Entrepreneurship at the University of Pennsylvania, and also the Jonathan and Linda Bressington Professor of Practice at the Department of Material Science and Engineering there. So before that, she was the Chief Commercialization Officer at DOE, and also the Director of the Office for Technology Transitions. She has also worked in McKinsey, actually started a company working on consumer products. Her contributions has been well recognized by many high-profile awards, including inclusion in the Time 100's 2024 list. So without further ado, let me pass it on to Professor Chen for this year's Wulff lecture.
The mic work? You guys hear me? Bueller? You see, the later we go, the less people know what that Bueller reference is, which is really kind of sad, where I know like I'm getting old. And are my slides up here too? Let's see. Thank you. So now the bar is really high. You didn't tell me how to be entertaining. And let's see if this works. I don't know if the clicker's working though. Okay, perfect. So I'm really thrilled to be here. Back in the day, I was sitting as a Course 3 PhD student. I can't believe now I'm here, and there's Christine Ortiz. I haven't seen in 20-something years. You look great in the same, by the way. You and I both look exactly the same as we did when we were 25, is all I got to say. And there's a couple things I want to do today. One is talk to you a little bit about why MSE is the major to be in. So if any of you guys are sitting here not sure what your major should be, Course 3 is where it's at, and if you don't believe that at the end of this, come find me and I'll tell you why, again, why Course 3 is where it's at. I also want to talk to you about the challenges and the beauty of materials commercialization. It's actually one of the hardest things to do, which is why I love it. So only those of you who are super smart and creative can be part of MSE, which is why you want to be Course 3, because the best and the boldest and the brightest are here. And then how did I actually do the work I did as the Chief Commercialization Officer at DOE to actually activate a nation to commercialize clean energy technologies? And then I'm going to give you a little bit of a secret, if we have the time, on the kinds of things that you guys should be thinking about as students over the next few years. So I think the first thing is to talk about, why is material science engineering really important? Because most of the pressing scientific problems are really looking at the limits of the materials that are preventing us from getting to where we want to get to. And therefore, breakthroughs are so critical in order to figure out where the world is going. Now, I don't agree with Elon Musk on everything, but I do agree with this, which is take material science, you won't regret it. So this is like very clear. It doesn't matter what your politics are, everyone agrees on one thing, which is material science is where it's at. So what is material science and engineering? It's something where people don't know about it when they are in high school. They all will say, I like chemistry, so I'm going to be a chemical engineer. But then when you realize you have to rotate your paper 90 degrees to fit the Navier-Stokes equation, you're like, tag out, and you're like, yes, come to material science. This is where some really great innovations are going. So I think about material science in three ways. One is using materials that have already been invented in new ways. Second is inventing new materials. And third is finding new ways to fabricate materials. Now, the great thing is people ask, well, where does this apply? The answer is everywhere, the entire world. No other major can say that is the case. Literally, any industry you're in needs materials, which is why, once again, Course 3 is the place to be. So if you take a look at what is shaping the future as we know it, there's a lot of mega trends, right, that are really at the heart of where the world is going. We're becoming much and more connected. When I grew up, we did not have these supercomputers in our pocket. We had to wait by the phone for people to call us. I know you don't understand what I'm talking about, but that is where we were. We're now much more connected. We have aging populations. We're worried about environmental impact and so much more. And it's really important because we need to innovate our materials to get there. So let me give you a couple examples of this. So when you think about cars, there are some mega trends where people are putting more and more electronics in the car. And you're wanting to be able to play Netflix while you are not driving and parked. But you want the ability to do that, right? That is taking more and more weight into the car. We also are wanting to improve the driver experience. So those are all great positive things that the consumer and people want. On the other side of it, there are standards on the CAFE side, which is really regulating how heavy cars can be because you have to reach a certain miles per gallon or a certain number of range, right, with an electric vehicle. So when you start taking a look at some of the trends and what's happening, the question becomes, if you're a materials innovator, how could you actually solve this problem by inventing new materials that go into a car? So an example of this are panoramic sunroofs. This is how it came about. Was there like, we need to take weight out of the car. There's a way to make lightweight glass. If you make lightweight glass, it's actually more fun for the driver because you get to feel more open when you're driving. And since you're able to take weight out of the car, you can put in more electronics while keeping the CAFE standards there. So I think the really important thing for materials is to think about where are there opportunities and barriers and where are the confluence of theirs that material science can actually solve that. If you start taking a look at other examples, one of the big challenges that they found in Bogota was that there's 700 tons of plastic discarded daily, but only 100 tons are recycled. So they had a huge issue with the amount of trash. At the same time, there was a shortage of homes. So there was a company called Conceptos Plásticos, which transforms plastic and rubber waste into construction material, basically giant Lego blocks, where they could then create low-cost housing. So they're able to create a 40 square meter house, 2 bedrooms, a bath, a living room, dining room, kitchen, which can be built by 4 people in 5 days for only $5,200. So that is all material science, right? And this is where you are looking to use materials in new ways. And in this case, the material was trash. Another example is sometimes you have a drink and it's way too hot to drink or it cools down too quickly. So this was actually a Penn person who invented a new material where they were able to find a material where the phase change happened exactly at the temperature where you want your coffee to be. So when you put it in, these coffee joules would basically absorb the heat and then retain the heat and discharge the heat so it would be at the perfect temperature. So I know that's kind of like a first world problem, but you can also solve first world problems with material science. And then one of my favorite unicorns is carbon, which was finding new ways to fabricate materials. So the holy grail in materials fabrication was how do you make super, super complicated parts? And there was a wonderful guy named Joe DeSimone who invented a new way to do 3D printing where he basically was able to do it in real time and has one of the best TED Talks ever that you should watch on material science, where he basically invented a way to do polymerization in real time to create really complicated 3D structures like the Eiffel Tower. And the holy grail is to get to automotive or other places where we can print on demand, but the timing and ability to create these was too long. And also to get into automotive industries and aerospace and others, it's really hard to do. So he actually went after the consumer industry first, and I was actually creating custom printed tennis shoes for Adidas. And so this is why I really appreciate Joe and the way he thought about it, was to actually go after industries that are easier to get into while you keep your line of sight to the hard industries. So while he's printing out tennis shoes, he's making money to get to the harder applications. So these are just 3 examples of how we actually can use and invent new materials, use materials in a new way, or invent how we actually manufacture materials. And that is what is the heart of material science and engineering. So if you take a look at these 3 aspects, in reality, they all are being done together. And so this is the phone I grew up with. And if you want to know, you pick up that thing and then you dial in order to use it. So if you take a look at what happened, we basically took using materials in new ways, inventing new materials, finding new ways to fabricate materials to create the iPhone. So the iPhone is all based on material science and engineering. So if you want your iPhone to actually work and be what it is, you need to be in course 3, which goes back to why course 3 is the best major, because you guys can't be without your iPhones. And all the things in red here are ways in which material science had to innovate so we could have this now for every single consumer who wants it. And so, give you an example, those of you who haven't had a chance yet to read Steve Jobs' biography, there's an entire section around the conversation he had with the CEO of Corning, Wendell Weeks, where what Steve Jobs wanted was to be able to use glass. Before then it was really polycarbonates being used, but he really wanted to have glass as part of the phone. And he had a board member who was like, well, you really need to meet Wendell Weeks, who is the CEO of Corning, and ask him to brainstorm with you. So Steve Jobs called Wendell Weeks up through the switchboard and was like, hello, this is Steve Jobs, I'd like to talk to Wendell Weeks, and got transferred over to the office of the CEO, and the assistant was like, do you have an appointment to talk with him? He's like, no. He's like, well, I'm sorry, he's busy right now. So then the Steve Jobs went back to the board members like, he's not interested in meeting with me. And so when Wendell heard the story of what happened, Wendell then called the Apple switchboard. It's like, hello, this is the CEO of Corning. I'd like to talk to Steve Jobs. Do you have an appointment? No. So then he went back and was like, he's not interested to talk to me either. But anyway, the two of them finally connected. And if you read the book, this is what Steve Jobs' glory was his ability to just cast spells on people and say, you can do this. And so what happened was Corning found some old technology that had been developed that allowed them to create a glass that could be made in very large form factors, and then a way to cut it so that it could actually be used for the iPhone. That's what Gorilla Glass is. And so I really like that story, and if you haven't had a chance to read the Steve Jobs biography, I recommend you do it. So this is consumer electronics, but if you take a look at any industry out there, material innovations is at the heart of it. You look at the first glasses that were there. You look at construction. You look at clothes. And you look at the evolutions. This is the first contact lenses ever invented. They actually were hard shell that went on your eye. And now we actually have implantables, right, that are restoring sight for people. Every single one of these all had material science at the core of it. There is not a single industry which doesn't need material science, not one. And so basically any industry that uses materials is game for any course 3 graduate, which basically is the whole world. So if you want to hold the world in your hand, you need material science. So now I've convinced you all to be material science majors. What I want to talk to you about right now is the challenges of materials commercialization. So pop quiz, who's this person? Raise your hand if you know who this person is. Hands up, higher so I can see it. Keep your hand up if you know this person is Thomas Edison. Keep your hand up if you know who Thomas Edison is. So raise your hand if you've heard of the name Thomas Edison. Raise your hand. Okay. Now keep your hand up if you know that Thomas Edison was the inventor of the light bulb. Okay. He actually wasn't. Jonathan Swan is the person who invented the light bulb. This man here. He was the one who invented a carbonized filament, which when you pass electricity through, gives off light. Thomas Edison was the father of the deployed light bulb. He was the person who figured out how to commercialize the light bulb. So he took Jonathan Swan's patent and figured out, how do we actually pull a vacuum on this? How do we manufacture this at scale? How do I actually connect them with utilities who at that point were delivering gas to homes? How do I flip them to deliver electricity to homes? Because if I want electric light, we actually need to be delivering electricity. So in order to have an impact in the real world, you actually need to deploy it into the marketplace. And an invention without deployment is a tragedy. An invention without deployment is a tragedy, because you've invented something where you may have a lot of paper publications, but it is not making a difference at all in the real world. And that is why it is so important to understand commercialization, because all of us have to be anti-tragedy. We have to get away from tragedies, which is why commercialization is so important. So what is commercialization? At the highest form, it's moving a technology from the lab or the dorm, because I know some of you undergrads are inventing things in your dorm, and then moving it all the way to the market. I see someone pointing at someone there. I'll have to talk to you later. And then, so how do you actually go from lab to market? First off is research, the invention itself. That's what Joseph Swan did. He invented the filament. So that's great, but then next stage is development, where you have this invention, you have this concept, and how do you actually make it into a working prototype, which is what Edison started doing, which is how do you pull vacuums so you have a longer life and so forth. Now that is great, but then you actually have to get to the last two stages of commercialization, which is demonstration, where you actually have to take the prototype and make it into a form where it could be used in the real world. Okay, and that is what you see here is a prototype that could actually be used in a real commercial application. And then you actually have to get to deployment where you are able to sell this everywhere at a price point that people are willing to pay for it and which the private sector can make money. That is what commercialization is. And note that commercialization does not go with, we do R&D and then we commercialize. R&D are the first two stages of commercialization. And the reason why this is important is that commercialization, RD&D, is not a linear process. It's a game of chutes and ladders. You can do research development, go to demonstration, and you find something out that puts you back into research. So we have to constantly be iterating, and we can't just be doing R&D and throwing it over the fence, because things will never make it to market then. And this is a challenge right now, is if you take a look at RD&D, we have 97% of the patents are actually failing and not making it through the development to demonstration transom. Only 3% of patents succeed. And one of the biggest challenges is we are not training our PhDs, our undergrads, our faculty, how to commercialize technologies. Instead, we're focused on the really hard technical issues that we have to overcome versus everything that needs to be addressed for something to make it to market. So let me give you an example of this. And one of the biggest challenges is in materials because of where we sit in the value chain. So if I've invented a multi-layer laminate, right, where there's some amazing material science, which is how do these two interfaces of materials actually work? How do we make sure they don't, delaminate? Really, 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 really hard science. And then now I'm deciding I'm going to put it into automobiles that a consumer can end up using. We actually need to, once we invent the materials, convince tier 1 manufacturers to use the material and to be able to create components which the OEMs will then put into the car, which then goes to the consumer. So our position in the value chain is so far away. We may invent something that's amazing, but if these people in between us and the consumer can't make money, we will never, ever have this be commercialized. It will never get to deployment. And so it's really important to understand how do we convince the entire value chain to actually adopt our new invention. And some value chains are really complicated. So take a look at the medical value chain, where you may invent something which is a material for a hip replacement. And if you use it, then the likelihood of infection, this is the invention you had, will decrease, and therefore the rehospitalization of a patient goes down. So that's good for the patient because the infection's less, right? And it's good for the physician because they have a happier patient. But this is where, the brakes stop. Everything, because you have to worry about the provider, the insurance company. The insurance company pays the physician today to do a job, which is replace the hip. And they pay a certain amount for that hip replacement actual product. They will not pay more to avoid hospitalization. And so if your material is more expensive than what is currently being used today, the providers will not reimburse for that. So you actually will not be paid for your invention, which is where policy comes in to say, hey, can you actually, insurance companies, look at a holistic patient and the holistic cost of a patient, and therefore we could maybe get paid. But that hasn't happened yet. So if you invent something where there is no way to get reimbursed for it because it's more expensive, then you won't get paid. So that also will never get commercialized, even if it's best for the patients. So this is the kind of stuff you have to think about. Now, the problem we have is that in commercialization, we have focused on technology because technology is hard. All of us who've gotten PhDs know how hard it is, especially in your third year when nothing is working and your advisor's yelling at you where your papers are. It's really hard. And our focus, right, has really been on something called technology readiness levels, where you say, I've hit TRL 9, that means my technology works and therefore I can get to deployment. Now, TRLs were invented by NASA in the 70s to launch rockets to the moon. When you're NASA in the 70s, you don't care about the cost of a rocket, you don't need a permit to land on the moon, you don't care about anything except does the rocket actually work? So the problem is that doesn't work for the real world at all. We didn't have a language for commercialization. So in addition to defining commercialization, when as Chief Commercialization Officers, research development, demonstration, deployment, we also need a new language so that people who were technical actually understood things beyond technology of what had to happen. So we created something called adoption readiness levels, which is a new language. And these are 17 different dimensions that are really talking about things beside technology that you or somebody will need to solve if you are actually going to make it to market. So for example, value proposition. That bucket are things like delivered cost. If you are going to make something, right, are you able to deliver it at a cost where every single player in the value chain can actually make money? If you can't do that, you will not get to deployment, right? Is it easy to use? If you have to retrain how people are actually putting a component onto a car when the entire automotive manufacturing is automated and you can't go into the current automation process, everything's a sunk cost, you also will not be commercialized, right? Next is around market acceptance, where is there demand? Do people want this, right? So oftentimes you get to these chicken and the eggs where people will not buy something that you've invented if they don't know there's an entire supply chain stood up. The supply chain will not stand up, like the tier ones and OEMs won't stand up until they know there's multiple people who want to buy it. So we have the chicken and the egg because they don't want to set up the supply chain until there's demand. The demand will not come until there's a stable supply chain. So how do you figure that out? In terms of resource maturity, we've heard about there's a shortage in minerals. There are workforce issues. Right now, if you take a look at nuclear, we have forgotten how to build nuclear plants. So if you want to scale nuclear, we actually have to build a workforce first who actually knows how to do this. Do we actually have the infrastructure that we need? If we're going to be doing hydrogen, there is no midstream infrastructure today, so that has to be built. And then license to operate, things like regulatory, permitting, community perception. You know, back in the day, the reason why we no longer know how to do nuclear is the community perception was nuclear was a bad thing. And that's why it went away. So these 17 dimensions are meant to complement TRLs and is the language around the other things you have to solve if you're able to actually bring something to market. So to give you some examples is applying ARLs to LEDs circa 2010. So in terms of license to operate, and this is the ARL framework, where basically for the 17 dimensions, we have a framework, and you can download this, it's still on the DOE website, where you check off, are you low, are you medium, or high? So in the case of LEDs around 2010, this is regulatory, which is, are there any changes or risks that we have around standards or requirements in order to deploy the technology at scale? And in terms of the license to operate, there was going to be a need, right, for an entirely new set of lighting standards and procedures by industry and government to ensure that there was a new way to think about product quality. That had not yet been developed by the industry. And so it was very high risk because the ecosystem had to figure out how to create these standards before LEDs could be commercialized. And mind you, LEDs were invented in the 1920s, right? And there was all these other regulatory issues that we had to figure out in order to get there. In terms of value proposition, ease of use, which is if you are a consumer and you're going to want to use LEDs, one of the most important things is you have to make sure that it's easy, you don't have to change all your light sockets. And so what the LED ecosystem was really good was ensuring that the A19 bulb was compatible to the E26 screw base that was being used for the conventional light bulbs, which meant that as consumers, you'd be willing to just do it because you know how to unscrew a light bulb and this one just screws back in. So these are the kinds of things you have to think about when you want to commercialize. You actually aren't worried about will the LED work. These are the things that are actually preventing things from making it to market. And then what you do is you basically do these ARL assessments, and you can download this from the DOE website. And we then combine these risk dimensions into a score. So what you do is you count the number of risk dimensions that are low, medium, or high. And then we very scientifically do a lookup table where you count and you say, what's the number of high risk dimensions? What's the number of low risk dimensions? And then what is my adoption readiness levels? And what you'll see is it doesn't take a lot for you to go from the perfect ARL 9 to an ARL 876 or 5. Because here's the rub, which is if there's one or two things that you need to figure out, you probably can do it. A VC or an investor will be like, okay, that's great. You have to figure out some of your unit economics. Okay, that's great. You have to figure out a little bit of the community perception. But then you're like, oh, and by the way, I don't have a workforce. Oh, by the way, we don't have this. Oh, by the way, I don't have that. Then your ability to make it to market drops off catastrophically. And so people who are engineers and deep in things saying this is not scientific, it's not meant to be. In fact, I don't even care if you get this right or wrong because there is no right or wrong answer. What you need is awareness of what needs to happen to bring something to market. Because if you don't know that awareness, then you don't know how to actually solve this. And if you're raising money from a VC and you're able to talk through all 17 adoption readiness levels, then they know you understand the industry that you're trying to get into. So, when you go into government, people tell you it'd be great if you can pass the baton and do a couple things well so that the next generation who comes in can use it and keep going. Like when you're cooking a big meal, someone steps in, they're the chef next. The great thing about ARLs is I think it's going to stick around because it has literally started to go viral. So here at, or back when I was at DOE, we used it to manage all of the money that many parts of DOE were getting so that we could really understand where we were on the commercialization transom and were we actually going to be using our money in a way that will advance products to market. The NSF TIP Directorate heard about this, so now all the innovation engines are using it. We actually had accelerators who have startups are now launching it. Investors are using it because this is a perfect framework for them to test whether or not the entrepreneurs know the answers to these. And if not, then they tell them to come back once they do know the answers. And then there's industries like the insurance industry. Geneva Association is the association for the insurance industry where they saw this framework and they actually created a new insurance risk framework for climate based on ARLs. And so for anyone who is looking to commercialize or really wants to understand how to have an impact in the world through material science, download the ARL framework and just think about your technology through it because it's really important to do that. So as a chief commercialization officer, one of the things that I need to figure out is how to bring technologies to market. And when I first joined and was called by President Biden to be the chief commercialization officer, we were really an organization that was focused on research and development. So this is from fiscal year 2020, which is the budget we inherited. And these were the highlights of what was in the budget that the first Trump administration had really focused on. And you can see it was really focused on research and development. And the only place they talked about deployment was for exascale computers. And now we have 3 of the 5 fastest computers in our national labs for DOE. But really, the $30+ billion budget was focused on the first 2 stages of commercialization. And we have 17 national labs, which literally would make Tony Stark cry with the amount of stuff that's in there. If you ever go to Oak Ridge, they have like a 3-story 3D printer. I mean, when I'm telling you, you go there like, oh my gosh, this is amazing, it's amazing. And they do amazing research and development. And then what happened in the first year that I was there was the passage of the Bipartisan Infrastructure Law and the Inflation Reduction Act. And those 2 hand in hand led to $370 billion being invested into the clean energy transition. So just to frame that for you, this is 10 times the annual budget for DOE was now being put into our organization to actually catalyze the commercialization of clean energy technologies. And many of the technologies that they wanted to focus on that Congress mandated that we try to commercialize were really around somewhere between the development and demonstration phase. And DOE had never thought about demonstration and deployment. That language wasn't there, that thinking wasn't there. And that is when it became really fun being the chief commercialization officer. And so $370 billion sounds like a lot of money, but it actually isn't. And in fact, to commercialize anything, you need the private sector to step up to do it. So we had a mantra at the Department of Energy. I reported to Secretary Jennifer Granholm, who is the most amazing human ever, super smart, amazing manager, and really a visionary. And she was like, we need to figure out how to use the money we got to catalyze the 23 trillion in the private sector. So we have $370 billion, but in the end, the 23 trillion is what has to activate, right? Those are the ones who are going to bring the technologies to market. So how do we do that? How do we convince them to actually commercialize these technologies which aren't quite there? And there was about a dozen technologies that we knew were going to be solving a lot of the issues around climate change. And the question was, how do we align every single value chain player in every single one of these industries so that we are on the same page of what it's going to take to bring these to market? That's a pretty big question, right? So there was a couple of things I was really inspired by in order to catalyze a nation. First was Gordon Moore. He created Moore's Law, where it was to double the number of transistors on a chip every 2 years. And in order to do that, we had to align everyone who was a player on the CMOS process, which was had competitors and multiple people across the value chain of how do we innovate the way in which we manufacture and design chips and do all that, so we actually can make this Moore's Law become a reality. And so Sematech created a roadmap that catalyzed the entire nation, the entire ecosystem on what we had to do, and we were able to get Moore's Law to happen. Next was the Manhattan Project, where we catalyzed a nation to build an atomic bomb. And we did it in a way that nobody thought we could do it this quickly. So I was like, how do we take Sematech, the Manhattan Project, and aim it to clean energy? And that was when my team at DOE quarterbacked the Pathways to Commercial Liftoff, which really was to, first of all, make sure that all the money being tied to demonstration deployment were being tied to the Pathways to Commercial Liftoff. So to give you context, my organization was tiny, like less than $20 million, 17 people when I joined. Friends of mine who were in other parts of DOE, I was like, keep walking. If you drop my budget, it's not even worth your time picking it up. But the key thing was, how do you actually influence other people to think about how do you actually use the money as effectively as possible? And coming from the private sector, having spent many, many years doing technology commercialization, I know how to commercialize technologies. And so I was like, if we can tie the money that you have gotten from Congress to our Pathways to Commercial Liftoff, then the private sector will start listening because they want the money. Next, we collected all the important data, so unit economics, projections on where the industry is going, all that. And by the way, not all the data was aligned. And that was part of the method to the madness is we actually don't know what data is right, but let's all get everybody's data and actually have a single source of data that we actually have awareness on what people are thinking about. We also need to engage stakeholders across the federal government as well as private. So EPA and others have equities in the stuff we're trying to do, so we had to make them on the same page. And because we tied it to the money going out the door, we were able to get people to come talk to us around what commercialization means. And then what we did was we created these pathways which were looking at the technology and adoption barriers for all these technologies to actually bring it to market. And when we launched all of the requests for proposals, like if you wanted money on hydrogen as an example, you had to have read the liftoff report, and people were coming with dog-eared copies because our question was, if we give you this money, how are you going to address these adoption barriers? And how are you actually going to activate the private sector to make this happen? So this example so I want to share an example of how we actually deployed this in hydrogen, where the direction from Congress on hydrogen was to stimulate the entire hydrogen value chain with emphasis on hydrogen hubs program to decrease costs associated with production, distribution, and consumption of green hydrogen. So they already were directing us, and they gave us $8 billion to create 6 to 10 hydrogen hubs across the nation, which would help to network the hydrogen producers, create the consumers, so the demand for it, and create the infrastructure in order to make this happen. In parallel, the Inflation Reduction Act passed 45V, which was a production tax credit. So for every kilogram of clean hydrogen coming off, you'd get $3 as a tax credit, which would really help because when you first are commercializing something, it's actually pretty expensive. So what we did was we said, okay, first of all, let's understand where hydrogen is used. And so we actually started doing a lot of looking at these are places where hydrogen is actually used and what the end use applications are, because you always want to start with the market to understand it. We then said, okay, given that, what is the end use willingness to pay? And what you start seeing is that there's some places like power generation where they're not going to pay anything for hydrogen. So it doesn't make sense there's a technology solution. But then there's other places like ammonia on the high end, it actually could make sense, right? Then you go back and say, okay, so if that's downstream, upstream, how do we actually make hydrogen? What are the different pathways? So there's steam reformation, where you actually are taking a carbon-based fuel, you're reacting with high temperature steam, and you're getting hydrogen and carbon dioxide off. Or there's water electrolysis, where you basically are using electrolyzer to split water into hydrogen and oxygen. And what are the costs related to actually go through these routes? And then the midstream, which is how do we actually go from producing the hydrogen and get it to the end user, and what are all the costs associated with it, right? If we're going to end up compressing it, what does it look like? Can we actually put it in salt caverns? And so all these unit economics were really important because, by the way, you know, I've had a senior design team who actually created hydrogen from water electrolysis and powered a little thing, right, a little car. So we know how to do it, it works, but the question is, how do you scale it to the point where you actually can get people buying it? And so, you know, one of the things we did was started looking at the adoption readiness levels and where risks were high and low. And using that, we could then say, here's the things that actually really matter to get our hydrogen hubs to work. We need to make sure our delivered cost is where it needs to be, right? Because right now it's really expensive, so how do we get there? We have to make sure we have midstream infrastructure, right, to get there. There's also community perception, because when we talk to people about hydrogen, what's the first thing people think about? The Hindenburg, right? It's like, oh my gosh, we can't be doing this. So these are the kinds of things that we had to grapple with if we're actually going to create a hydrogen economy. And you know, we basically then looked at the value chain and said, okay, we go from production to midstream to downstream. And what are all the challenges that we have to address in all these different places? And we worked with every single, you know, people and stakeholders who were across this and companies. So we all got on the same page of here's what it needs to look like. Here's what the unit economics need to look like. Here's the barriers we have to overcome and so forth. And when we did this, the thing that was really exciting was in the case of hydrogen, and it's true actually for many materials that you're trying to commercialize, is the offtake agreement. So an offtake agreement is basically when someone promises they're going to buy whatever it is that you're making, and they have a long-term offtake agreement, so you are guaranteed revenues, and therefore you won't be scared of creating a supply chain where you end up making all of this and no one buys it. Now the challenge is that whenever you're doing something new, it's not yet at scale, so electrolyzer costs are too high, there's all these issues, and so what happens is we can't guarantee what the cost is actually going to be for the hydrogen coming off. And so if you're going to do a long-term offtake agreement, what price do you guys write the contract on? Because if you write for a certain price, let's say $2.30 per kilo, but then when the hub starts getting set up, it's like $2.80, then who's going to pay and suck in that difference? So having done the liftoff report, we said, you know what? We got $8 billion from Congress. Let's take $1 billion of that and actually use it to help with the contract for differences, because we do not know what the cost is going to be. And this is the first time ever the federal government actually did a demand side activation. Normally they focus on the supply side and the money is used for that. This time we said we need to help the hydrogen demand. So we had to work with the White House and Congress and get them comfortable with why this was important. And we created the first ever federal program to help with demand activation. And that is what allowed us then to actually get people to sign the offtake agreements, was they knew that there was $1 billion for the contract for differences, which is how this then got activated. So this is the kind of thinking you have to go through and innovate within government, because people are like, well, we've never done that before. I was like, well, why not? We can. Let's go talk to people and you get it done. And so it'll be interesting to see how this hydrogen stuff comes through, but this is an example of how we use the Pathways Commercial Liftoff to catalyze everybody to get on the same page. And we did this for a dozen technologies. So if you go to liftoff.energy.gov, that's liftoff.energy.gov, you can download these reports, there's webinars, and you can see all of the work that we've done on the pathways to actually bring all these technologies to market. And for all of them, there's some, killer slides, as I call them, in terms of some take homes. Nuclear, one thing that was really interesting is here in the US, we actually have 50 first of a kinds. Every single nuclear company has their own way of doing things, and that's why you haven't been able to scale. And if you look at France, they didn't do that, and that's why they have a nuclear industry that's thriving, and they're able to choose one design. If you take a look at long duration energy storage, we saw that we actually had to decrease the costs by 45%, and then also improve the round trip efficiency from an engineering standpoint of the actual materials, 7 to 15%. And if we can get that to align with the market regulatory mechanism, that's when we get to liftoff. And liftoff is defined when you have a technology that is economically viable and it no longer needs the support of the government to actually be part of the market. The one that got me the most upset and scratching my head was Innovative Grid, where we basically mapped out the value chain for the grid and understood where there were innovations of things that could be done. And what we found was there were actually materials innovations like reconductoring, where you change the materials that are actually in the wires, dynamic line rating, where you use AI to figure out how do you balance supply and demand. All these technologies have no risk around them. In fact, we did analysis showing that the ROI on these, the return on investment, was extremely favorable, and utilities could actually make money if they deployed them now. And in fact, if you deployed it, you could increase the current capacity of the grid by 30%. But none of these have been deployed because the way the business model's been set up, utilities are not paid for fixing their existing infrastructure, they're paid for new stuff. So now we have an issue where we need to figure out how do we actually help the utilities deploy the stuff. But every one of the liftoff reports goes into this kind of depth. So if you're trying to commercialize any of those technologies, I really highly encourage you go there to liftoff.energy.gov to download these. So what's been the impact of the work that we did over the last 4 years? Well, we want to be private sector led, government enabled. For every dollar of public money coming in, we got $6 of private sector. That's amazing. So $7 billion from the hydrogen hubs catalyzed $42 billion in the private sector. We also created over 1,000 new and expanded clean energy facilities, over 400,000 jobs, and most of these were in red states. 90% of the money from bill and IRA went to red states. And then we put the equivalent of 30 Hoover dams of clean electricity on the grid last year. 30 Hoover dams. So, it's been really kind of interesting, right, to see the impact that we're having. And I'm confident because of the fact that we are focused on trying to find new forms of electricity that are going to be economically viable, creating jobs and all that, that this will continue. So I'm going to very quickly run through a couple of things I want you guys to listen to for the students who are there around what you should focus on the next few years. Okay, so you guys all got in here because you're top of your class, you're A+, blah, 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 blah. Okay, great. Guess what? That doesn't matter. What really matters is you do what you love. And in fact, if you have a 4.0 GPA and you're triple major, I actually won't hire you because you spent all your time studying and not doing what you love likely, so just keep that in mind. So how do you know what do you love to do? Well, let me share with you what I love to do and how I got to where I got to. So all of us love technology, right? Because we all got, we're here at MIT. You can't not love technology, be at MIT. It'd be kind of weird. You go to the other school if you don't like technology. So after doing technology, I then went to McKinsey & Company and learned business. And actually, my very first study was a technology commercialization study where I learned how to bring technologies to market, which was really where I spent 13 years was just commercializing technologies everywhere, from medical devices to metals and mining to consumer electronics to consumer products, all kinds of fun things. And the other thing that's always been at the heart is making. I love making things. I'm a maker. I knit. I make jewelry. I make these insane birthday cakes with my children. Or I used to. They are now 16, 19. No longer want to make cakes like that. But I love making things. In fact, I love making things so much I just started a pottery studio with my friends called Rebel Potters. And we started in September. We already have 83 students, so it's also a little bit crazy. But this is my Venn diagram of what I love. And so I need you to ask yourself, what is your Venn diagram? What is it that you love? And you may say, I don't know, I'm 18 right now and I just need to figure out what classes I want to take. Well, guess what? Get outside your comfort zone. Go do something new. Go try new things. Because the secret of material science and engineering is it applies to everything. And so if you're looking at potential Venn diagram circles, every single thing here can have a materials angle to it. So the question I have is, what do you love? There was a person at lunch today, is he here, who loves biking? Hi. So, you know, I was like asking him, what do you love? And I was like, hey, do materials. He's like, what? I can do materials and biking? I was like, biking is all about materials, right? Do that as your Venn diagram. So ask yourself, what do you love? And continue to double down on that while you're here, because that's where your magic is when you do something you love, is when people beam and you have high energy. So that is really, really important. Then once you figure out what you love, figure out where can you be different. Like my superpower is because I've gone to places where I'm different. So when I was at McKinsey, all those folks are filled with, you know, that other place that does MIT stuff with business. They're all full of those guys, not the classical, you know, PhDs like us. And I knew technology, so I could speak with technology when they could only speak business. And so I became really well known for technology commercialization because I could meet with CTOs and spar with them in a way that MBAs couldn't, right? So that is what made me unique. And then now, you know, when I'm at Penn, I'm the person who knows business and the other people know technology, right? So where in your Venn diagram can you be unique? And then where can you actually go and use it? So when I was with my private sector clients, it was all about technology. Now that I'm academia, it's all about the ability to think about business. When I was in the public sector was full of PhDs, R&D for DOE, and so it was my private sector thinking that made me unique. I also did a side gig where I went and launched my products on QVC, which was really fun. I think I'm the first presidential appointee who also was on QVC. I may be the last. But anyway, this is how you have impact, is when you figure out your Venn diagram, you figure out what you love, and you apply it to places where you are different. And it's really important to expand your network, because when I decided to leave McKinsey to launch a Kickstarter campaign to try to get on QVC, they all thought I was having a mental crisis breakdown. Man, her middle age crisis is really weird. So I went and found startup entrepreneurs to talk to, like, oh, it's great to be here. I found people who had been in the private sector and in big companies who went to do their own startups. And that gave me power and the strength to actually do something that people thought was crazy. Also find your voice and advocate for yourself, because people like to do things in the status quo way. So they'll look at things and say, oh, yeah, you don't fit there because you're not this, you're not that, especially if you're trying to be different. If you're an orange in a sea of apples, they're like, we can't have you do this because you're an orange. So, you know, an example of this was, you know, here I am, a purple duck, a professor of practice who is basically a second-class citizen in the academic world because I don't have tenure, I don't do research. But when they were looking for a new undergrad chair, the chair of the material science engineering department at Penn had known me since I was 17. And she came to ask me for advice, was like, hey, you know, who should we have as an undergrad chair? And I was like, well, what does an undergrad chair do? It increases enrollment, and it also, for material science, it also changes curriculum. As we're going through all the people, and finally I was like, what about me? And she's like, what about you? And I was like, I'd be awesome. Yeah, but you're a non-tenured, non-research professor. Now this is a sponsor of mine who was telling me, she didn't think about me for this. And I was like, does it say somewhere I can't do it? She's like, no, but nobody else is doing it. And I was like, can you check? She's like, okay. So she goes and she looks, well, nowhere official does it say. So she went and convinced the dean that they would do this for 1 year because a person that would have been a good number 2 was too busy doing some other stuff. But after I knocked out of the park, and it really helped, ABET came to review us that year, and ABET was like, everything Vanessa's doing, you guys need to do more of. And so then I ended up staying as undergrad chair. I am now Vice Dean of Innovation Entrepreneurship, also not tenured, also a purple duck in a sea of yellow. But you know, when I came back, I was like, I want to disrupt things. Give me a title so I can go do that. And so you have to ask for what you want, because even people who support you've known you for a long time may not think disruptively. And the last thing you have to do is dare to do things differently. Everyone wants to do things the way they know how to do it, and that is just not fun. You need to look and see where there are problems and how you might be able to fix it. Because if you are able to, you know, find sponsors, figure out what you love, expand your network, ask for something, now you have to figure out, how do I do that differently? And you know, we were able to do that when we were kids, right? We look at something, why is it that way? Why can't I have, you know, dessert as an appetizer? I don't understand. Why can't we do that, right? And then you have your North Star, which is, you know, how do you actually want to navigate things? And if you can figure out why are things a certain way, ask yourself, how would you do it differently? Then you actually might do things differently. And as kids, that's what we did, right? There are stairs that everyone walks up, but hey, I'm gonna go this way. This was my daughter who, was like, this is what we're gonna do. And so we have lost that magic the older we get of doing things differently. And so, just as a quick recap, what I've told you, if there's only one thing you're going to remember, it's material science is the major to have, right? Material science is a major to have. If you guys want an impact in the world, go to material science. And like I said, if you still haven't figured that out, I don't know what to tell you. Next, to bring things to market, you have to go through research, development, demonstration, deployment. And we are teaching research and development. We're not teaching how to get through demonstration and deployment, but we have ARLs that you guys can download and liftoff reports that'll get you partway there. Find what is it that you love to do. Focus on that and don't spend all your time studying and being in the lab. Do what you love. Find a place to be unique. Expand your network, advocate for yourself, and challenge the status quo. And if you can do these things, I am very confident that you guys will have impact in the world. And so with that, I will take any questions. And this is the mascot I created when I was at OTT, the Office of Technology Transitions, because there's too many acronyms out there. So I was like, I came from a land of beavers, and I might as well come to a land of otters, OTT. And everyone's remembered because, otters are friendly animals who have a positive impact on the ecosystem. And we called her Sam because she's small and mighty, because even though I'm tiny, I can have a big impact. And so I hope that also inspires you, which is you don't need a title, you don't need the money, you don't need the people. You can still have an impact in the world if you do the things that I told you to do and dare to think differently. And so with that, I'll take any questions.
Thank you. This is certainly one of the most entertaining, also most inspiring Wulff lectures I've been in. So, okay, floor is open for questions.
Thank you for your talk. The question I had was, clearly over your career, you've had a lot of different chances to do very different things. And those transitions can be really scary, especially when you're the one and it's your life that you have to do it with. How did you know when you were getting to those transition points that you needed to do a transition or that it was the right thing to do?
Yeah, that's a really good question. So a couple things is I have a really supportive ecosystem where when I'm not happy, it's pretty obvious. And there are like, a lot of self-reflection with my parents, friends and all that kind of stuff. And so, and the other thing for me is my North Star is learning. So if I'm not learning anything new, I get really bored and I end up being pretty unhappy. And so I think at the point where I'm not learning something is when I know it's time to change. And the reason why I decided to do the Kickstarter campaign was my then second grader had invented something, and her school was putting them through an entire entrepreneurship program starting in pre-K. So she had done her little pitch, which she actually did on crayons, because she said PowerPoint's boring. My mom does it all the time, so I'm going to do my pitch using crayon. And she did an entire pitch around her hair hug invention. And I was watching this going, if my second grader can do this, why can't I do it for my inventions? And I just decided to do it. And I gave myself a time bound, which is I'm going to give myself 2 years to do this. I will always be a former McKinsey partner, always have had a PhD or MIT, I'll get a job somewhere, and I'm just going to go and do it. I think the other thing that I will tell all of you is, I was a grad student here making $18,000 a year. That's how old I am, because I know it's a lot more now. But I always lived well below my means. So we always were very fiscally conservative. So we banked one of our salaries, like up until less than 10 years ago, we lived in a house where the 4 of us shared a bathroom, right? And so when you have financial flexibility, it also gives you the power to try new things without being worried that you have to go hit a mortgage or that you've got 2 mortgages and a boat and a blah, 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 right? So I think that's really important, is when you've got financial freedom, it also gives you the ability to take more risk. So I think that's the other thing that's been really important. You're gonna get your steps in.
Thank you for the mic. Thank you for the wonderful talk. It was really nice. I'm really wondering, do you have some kind of hopeful message about the future of the climate and sustainability in the US and what's coming for us? For example, I'm finishing my PhD working on exactly scaling up climate and sustainable solutions. And I was really hoping to work in national lab. And now I'm like, what is going on? So as an insider and person who knows a bit more on the inside, do you have any perspectives to offer and like give us some hope?
Yeah, so really good question. And I think what we need to do is take a big step back and ask ourselves, what is it that every administration wants? We want America to be thriving, right? We want to be competitive. We want to create jobs. We want to make sure things are affordable, right? All those things are important. And that is why the Pathways to Commercial Liftoff, when I focused and wrote these with my colleagues and others, there's no policy in it. Because in the end, to commercialize anything, you need it to be affordable. And so in the end, policy can help drive the affordability, but how do we get there? What is the pathways to it? So I think the really important thing to think about is, what makes America great is like we've got amazing R&D. Our national labs are crown jewels, and that first pie chart I put up was actually Trump's words around talking about the national labs and others. And so I think it's really important to just focus on where we have commonalities and not where we have differences, and think about where can we actually make sure we're on the same page. And so, like I mentioned, the majority of the money coming out of Bill and IRA went into red states. And so if we were to unwind that, if this administration was to do that, that really would be political malpractice, because you're going to be harming the states where we actually are creating jobs and doing these things. So I think, we're only, less than 2 months into the new administration. I think it's really important to just stay the course and, do what you do. And then let's see, what happens a few months from now when the dust settles. Because I still think that the new administration and Congress and the different agencies are still trying to figure out their relationship. It's still early days right now, and so it's really hard to predict what's going to happen when you are early in a relationship. Just like when you're dating, are you going to marry the person? I don't know. It takes some time to figure it out. So I think there's some time right now to figure out how the relationships and dynamics are going to evolve in DC.
Hi, sorry. I wrote my question down because I knew I would be nervous.
You're doing
great. My name is Jeannie, and I'm a third-year undergrad. I'm super undecided about what I want to do in the future. I'm really inspired by your talk, and I completely hear you about going out and doing what I want instead of studying, getting a perfect GPA. But earlier today, I was sitting in entrepreneurship class, and I heard you mention that you wouldn't be where you are without your PhD. So what's your take on how your PhD has contributed to where you are today, and how should we undergrads who might be really impatient and eager to do something in the world decide whether or not to get a PhD?
So I think getting a PhD is a very individual decision. And if you're going to get a PhD, do it because you find a topic that you love and you found an advisor that you really want to work for. If you don't have a topic that you love and you haven't found an advisor that you really want to work for, do not get your PhD, because it's 5 years of a lot of work, not a lot of money. But I will tell you that for me to have had the impact I've had, being able to understand what it takes to actually invent something and do research was really important. Because without understanding how research works, which is the front end of commercialization, I would not have been able to understand the back end, which is why MBAs can't do what I do, because they have never understood the technology to the level that a PhD does. So I think it's really up to you about what you want to do, right? If there's some places you need PhDs, there's other places that you don't. But in the end, the number one thing is there something you really want to spend 5 years thinking about? And is there a professor you're excited to work for? If you can't answer yes to both of those, I would do it personally. But ask many people, because you'll talk to someone else who's like, I completely disagree with Vanessa. You should go do this. And neither of us are right. We just have our biases, and you have to figure out for yourself what makes most sense for you.
Thank you.
Hi, thank you so much for your talk. So during your ARL's discussion, you mentioned them as like a new language for commercialization. You also emphasized like what's the common language between political, different political perspectives. I think as a PhD, we're kind of taught that we need to learn like there's a very specific language in academia. There's a specific language in our field we need to learn. So I guess how did you like learn? How did you have like the courage to like devise like these, I guess, new languages to like push forward something, like, if that makes sense. Yeah.
Yeah, it does. So when I was at McKinsey, I learned business, and because I was technology and business, I saw there was a gap, right? And so I'd already been thinking a lot about this, but realized when I was at DOE, I now had a national platform to actually do something. So I think DOE gave me the courage to be like, hey, if you really want to change something, this is the time to do it. Because unless you have a national platform, it's really hard to do it. And so that's what gave me the courage. And I like to be the upside down owl. So I was like, let's do things differently and let's see if this makes sense. And because of the fact that there hasn't been anything like that before, this is why it's going viral, is because there's been a need for it. There's been a gap in language on this. So that's what gave me the courage to do it.
Thank you.
Hi, I'm Neha. So you had a graphic where there was someone tinkering on some machine, and then there was a lot of people just laughing at them or staring or pointing. And I was curious, so I'm sure you've had a lot of ideas that people didn't agree with in the moment or they didn't think that it would work. So in order to actually have an impact, I'm sure you had to convince those people. So what's a time that you had this idea that you knew would work, and what did you do to convince everyone else that it was going to work?
So I think the really important thing is that when someone has a different viewpoint, they're not wrong, right? All of us have a different way in which we've been brought up, and therefore your viewpoint is shaped on your life and the experiences you've had. So the fact you think one thing is not wrong, it's just different. So I think that is why we have such an issue in our country right now, is that we have political parties who say the other one is wrong versus understanding their truth, right? If I'm a single mom who's doing 3 jobs trying to put food on the table, I don't care about climate change, right? That is not top of mind for me. I don't care about transgender because I am struggling right now to support my family. And that is the things that matter to me the most. Is she wrong? No, that's just not her reality right now, right? And so for me, what I try to do is really understand someone's reality and understand why they're thinking the way they do. And one thing I tell my entrepreneurs that I mentor is that we're born with 2 eyes, 2 ears, and 1 mouth, and we have to use it in that ratio. Because we spend too much time telling people why we're right, and we're not spending enough time understanding why they're thinking what they're thinking. So if someone is really against or on a different side of you, instead of trying to keep telling them over and over again why they're wrong, you have to ask them, well, why do you think about that? Why is it there? Why? And go down all the whys until you understand their truth. And then you can be like, okay, I understand that. Now let me explain to you why I'm thinking this way. And then you get to kind of hopefully a meeting point. And so when we're doing these pathways to commercial liftoff, there was a lot of discomfort in DOE around this, because the way in which we do things in the private sector is very 80-20. We do not need rigorous numbers. We do not need any of that stuff. We are like, is it directionally correct? We'll make some decisions. DOE is full of very classically trained PhDs, like us, and doing an 80-20 feels wrong. Like, they have done reports in the past where they spend 4 years vetting the numbers. We did our liftoff reports, like the first 4 we did, hydrogen, long duration energy storage, carbon management, and nuclear. I chose those 4 because there were leaders at the other parts of DOE who understood what we were trying to do and were willing to help me guide their teams against this uncomfortable way of doing things. But my team had to spend a lot of time with folks who thought what we were doing was wrong. And that was okay, because their truth was, we're PhDs and we have to do this because when we're doing experiments, we have to have rigor behind it. And so we spent sometimes days on figures in the appendix that would not change whether or not the private sector would activate, but we had to go through it to drive the comfort of the R&D folks who really understood like hydrogen, so that they felt heard and we were actually understanding where they're coming from. So I think that's a really important thing, and why I think our nation is having such an issue right now is we're not spending enough time understanding other people's truths and why they feel a certain way. And that's where I think it's really important not to feel like your truth is the only truth, because it's not. So that's how I approach this.
Thank you.
Okay, so I would just want to mention that if you have more questions, we're actually going to have a reception session in the chip room after, and you are definitely feel free to raise more questions to a speaker. And we also have a special gift
Oh,
for speaker today.
thank you.
Yes, so I'm Yatming Chang, and in addition to being a faculty member, I'm an alum of DMSE twice. And this is a MIT DMSE exclusive,
Ooh.
and you can tell
Can I sell it on QVC?
you won't want to because it comes in a bag that says DMSE.
That's awesome.
All right, and so small token of our appreciation and thanks for coming and sharing your experience, your wisdom, your inspiration with us.
Oh, wow.
And I'm glad you kept that up there.
Oh, I think I'm about to be very happy. Oh my goodness. That is amazing.
All right. The MIT mascot
With my OTT mascot?
from the MIT Glass Lab.
Oh, it's from the MIT Glass Lab?
It is from the MIT Glass Lab.
Oh my
and
gosh.
it's engraved in Wulff Lecture 2025.
That's amazing. I'll need my reading glasses because I can't see. But thank you.
Thank you.
very much.
Thank you again.
Thank you. This is amazing. Okay, thank you. Oh my gosh, this is an amazing gift. Thank you.